Hello, everybody. Today I'm going to run through multinomial logistic regression and binary logistic regression. Binary logistic regression is sometimes and often just referred to as logistic regression, so I might do that occasionally. So as you can see, this is a random data set that I'll just be demonstrating with you. So first we're going to do multinomial logistic regression. We go to Analyze, Regression, and then we're going to go to multinomial logistic regression. As you can see, I've kind of already set up the variables. My dependent variable is a 3-level variable. Let me show that to you real quick. It's living, which is a self-reported variable of where they live, the values. There are 3 levels to this categorical variable: urban, suburban, or rural. Just particular note for this, rural is coded as 3, so it will be our reference category. So again, regression, multinomial logistic regression, living, and you can double check to make sure that that level 3, that last variable, is the reference category, because you can see in parentheses it says last here. So I've loaded all of my predictor variables into the covariates: age, education, income, and physical symptomology. So then we're going to go to statistics, and we're going to make sure that information criteria, so that we can get that Akaike score, the AIC, and classification table, and goodness of fit. And in the parameters, we want to make sure that estimates and likelihood ratio test is in there. Click continue, and then okay. So we get a good amount of output here. Let me see if I can open this. Here we go. So first is the fit of the AIC and the log likelihood, the Akaike information criteria and the log likelihood. The Bayesian information criteria is similar, but to the AIC score, but it's not necessarily, it's not something that we look at here. So we see the AIC, the intercept only, is basically the null model compared to the final model, which includes all of our independent variables that we loaded in. And you want that score to be lower, that final model, which indicates an improved model fit. So here, the AIC and the log likelihood, you see that it does, in fact, decrease, which is good. So next we look at the log ratio test. Well, we could look at the pseudo R-square first. Sorry, let me pull up the output again. I lost it. There we go. Make sure I'm sharing this entire screen. Okay, here we go. So model fit, again there. The goodness of fit, the Pearson is the chi-square. We want that to be statistically significant, so less than 0.05. As you can see here, it is not. The pseudo R-square is the amount of variance explained, and being able to discriminate between the 3 groups. Sorry, there. You can see we explained 9.6% of the variance, not a whole lot. We move to the log likelihood ratio task. So each of the variables we included and how those contribute to improving or reducing the AIC and log likelihood ratio. We can see that age does, because it's statistically significant. Education does, it's statistically significant, but the other 2 do not. The next box is the parameter estimate. How you interpret this with a multinomial logistic regression is you take each large row in turn. So each parameter is the likelihood of being classified as urban compared to the reference category, which is rural. Again, that was the last level, which was 3 for rural, and suburban compared to rural. So the likelihood of being in either one of those categories. This is the parameter estimate, the linear parameter estimate, but because this is a multinomial logistic regression, that though we report it, it means absolutely nothing. What we interpret is the exponentiated parameter estimate, which is the odds ratio. Finally, we move to the classification table. And as you can see here, the diagonal is what was accurately predicted. And this model does a really, really poor job, though overall it's better than just completely random, which completely random is 100% divided by the number of levels in your categorical variable. So for us, 100 divided by 3, because there are 3 levels, is about 33%. So you can see that 60 is better than 33%. However, when you look at these individual rows, urban and suburban, I mean, we're doing a really, really poor job. We're doing far worse than random. So it kind of makes sense that our fit statistics up here, our chi-square, and our ability, the percent that we're able to explain, is not very high and not statistically significant, because we're not really accurately explaining as much as we should. So next we're going to move to a logistic regression. We go to, binary logistic regression. We're going to go to regression and then binary logistic. So I've already loaded in here some variables. We're looking at gender as our dependent variable, which is not always an ideal thing to predict, but in this case, this was the only binary code I have, so just work with me. Then income, age, do you have a computer or not? Sorry. And then symptoms, severity. You can see computer or not is categorical. It's a binary variable. So in you can click categorical and just move whatever variables are categorical over. And thankfully it marks it here for us so we don't forget. Then we're going to go move to options, and we're going to want to make sure to click this goodness of fit. We do not need the classification plots and the confidence interval as well, and we're also going to include a constant in the model. Click OK, and again we get a series of output. Forgot to also say that when we're doing the assumption testing, let me show you where that is real quick. Regression, binary. Go to save options, and here are your studentized and standardized and Cook's and leverage values right there, and you would just click those and save, and that would be for the multinomial logistic regression, and you can also do it for logistic regression. Okay, back to our output. So the first variable is just kind of looking at, the first block is kind of just looking at the number of missing values. As you can see, I have quite a few here. Then we're gonna move down a little bit, and block 0 is the beginning block. It's basically the intercept block or the null block, and this one is not going to have any of the output for us. We move down to block 1, and we could see the model summary here for the log likelihood ratio, and the pseudo R squared is all in this model summary block. Also, we see the omnibus test for chi-square. Then we're going to move down to this Hosmer and Limashow test. We want this chi-square to be statistically significant. And we see here that it is not. I already pointed out the omnibus test. We want to look at the model. And again, we want that to be statistically significant. This is a model fit parameter. And we want the log likelihood to be lower. Then we go to the classification table, and like the multinomial logistic regression, the diagonal here is what we predicted accurately. Also similarly to the multinomial logistic regression, we have 100% accuracy. We have some problems with one level in particular. So the percent correct for men is at 0, and the percent for women is 1. The overall, yes, it is better than random, which is 50%. But again, the specific lines, there's some existing problems there for sure. So finally, at long last, we come to the parameter estimates, the variables in the equation. So we see income, again, like the multinomial logistic regression. This parameter estimate is a linear estimate. We cannot interpret this. So we use the exponentiated B, or the exponentiated parameter estimate, which is the odds ratio, and we can interpret that along with the 95% confidence interval. So we see that the only variable that predicts, it's not really a variable at all, it's the constant, or the intercept. So no wonder our model fit is a bit of a disaster, because all the variables that we have in this model are not significantly predicting classification or the odds of being man or a woman. Please let me know if you have any questions.